Good evening everyone. Today we are going to see the solution for this multiple choice questions of numbers 8, 9, 10 in continuation of this last video where we solved this 7th question. Okay, these questions are there in unit number 3 magnetism in class 12. Okay, so right away we'll go to this next question. So this is the question actually. A wire of length L carrying a current I along the y direction is kept in a magnetic field given by B vector is equal to beta by root 3 into IJK Tesla. The magnitude of the Lorentz force acting on the wire is. Okay, so actually this is a wire. Yeah. So this is actually the wire of length L given the problem, and they are saying it is in the y direction. So I can take the unit vector along this y direction is j. So I can say this one as L vector. Okay, L itself, length itself I can say is a vector. Okay, this multiplied by this unit vector j. So as per the Lorentz force formula, the force acting on the wire, okay, on the wire which is kept in the magnetic field. Okay, so this wire is inside the magnetic field, so the magnetic field will be like this. So that is into this page like this, perpendicular to this wire or some position. Okay, so this magnitude of this magnetic field is given by B vector. So this is by beta divided by root 3 into I j k. So this is the direction of the magnetic field B. Okay, B vector is equal to beta divided by root 3 into I j k. This is the direction of the magnetic field, and the direction of the current is towards y. Okay, along this y direction. So as per this Lorentz force, okay, Lorentz force which is being created or on the wire will be okay IL into B. Okay, this IL into B vector. So this is a cross product of current into length of the wire and into B vector. Okay, so this one we can write it as I can write it as L into j cap, that was given here, cross product of B vector. B vector is given as B by beta by root 3 into I plus j plus k. So this is the two vectors, so I have to take the cross product between this. So this one I can write it like this. I can take this IL and beta by root 3, okay, because they are like a scalar or a constant, I can say I can take the outside. So beta by root 3. So I should take the cross product between j cross and this IJK vector, I plus j plus k. Okay, so this one I can write it as beta root 3 I L, okay, into this I have to take the cross product between j and these three vectors. So j cross I, you know it is minus k in the opposite direction, because it is in the opposite direction. If I take the cross product if between j and I, it is minus k. Okay, and if I take the cross product between j and j, it will be 0 cross product, because angle between j vector and j vector is 0. Angle between this is 0, theta will be 0, so sin 0 will be 0, so that will be j cross j will be 0. Then j cross k will be I, because in the cyclic form jk ijk, so in the cyclic form so it is plus I only. So now if I find out the magnitude of this one, magnitude of this vector, that will use the final answer. Okay, so beta by root 3 I L into minus 1 square plus 1 square root of, okay. So this will become root 2, okay, this will become root 2. So finally I will get it as root of 2 by 3, okay, root of 2 by 3 into beta I L. So this is the force, Lorentz force or magnetic force, Lorentz force acting on this wire, length of wire which is having length L, and it's along this y direction. The force acting on it will be this much of newtons. This much of Newton force will be acting. So the answer here will be this one. A option is the right answer. Okay. We'll go to the next question. So here the ninth question. A bar magnet of length L and magnetic moment Pm, okay, is bent in the form of an arc as shown in the figure. The new magnetic dipole moment will be. See, what is a magnetic moment? See, if I take a bar magnet like this, okay, which is having a pole strength of Qm, this is having pole strength of Qm, and the length of the magnet is L, then I can say define this magnetic moment. Okay, magnetic moment of this bar magnet will be Qm into L. Okay, so this is called this effective L, effective length. Usually it will be taken as 2L, but in the problem itself they are given the length of the magnet is L itself, so I can take like this. So Qm into L will give the magnetic moment of this. So the same bar magnet, this has been bent like this. So this is the same length of, okay, this bar magnet is bent like this as per the diagram. So this, you can see this diagram. So this diagram is bent, and this magnet is bent like this, okay, and which is having that arc length of R, and this forms an angle of 60. Okay, so here, so this diagram solution. So if I take this as R and this is R, and this is, I have to find out this length. If I find out this length, I can calculate the magnetic moment of this magnet, okay, which is having the pole strength of Qm and Qm, for example, if I say, okay. And this length, if I in this triangle, if we say this is 60, means this angle and this angle should be equal, okay, this also 60 and this also 60, and this length also should be R, because it should be equilateral triangle. So this R, this R, and this also should be R. So my new for, see here, this length, this bar magnet, this length will be R, okay. So now new magnetic moment for the bent magnet will be what is having a pole strength of Qm, this also Qm, so this R, so it will be Qm into R, okay. That is new magnetic moment for this bent magnet will be Qm into R. So now I have to find out R, okay. So if I want to find out this R, okay, so assume this is a bent magnet, so the length of this arc is L, and this one is 60 degree, and this one is R. If I find out R, then I can substitute here and find out the value of new bent magnetic moment of this new bent bar magnet, okay. I have to find out this R. So what is the relation between this angle R and L? It will be R into this theta, okay. R into theta will be equal to L. So this implies this theta is 60, so the 60 I can write it as pi by 3, okay. So it's 180 by 3. So why? Because if you see the options here, I have some values of pi and all, okay. This 4 options. In terms of if you see the 4 options, no, you have in terms of Pm only, that is this unbent bar magnetic moment, okay. So I am writing this theta is in terms of pi, so R into pi by 3, that will be equal to L. So this implies R will be equal to what? 3L by pi, okay. This, so now you substitute in this value, so here, so if I substitute here, pneumatic moment will be equal to qm. Instead of this r, you substitute this value 3L by pi. So this one I can write it as 3 by pi into qm into L. What is this qm into L? That is unbent magnetic moment. Unbent, okay, the straight magnetic moment is qm by into L. So this one I can write it as 3 by pi into pm. So this is the pneumatic moment of the bent bar magnet. So the answer should be this one, B. So B option is the right answer. Okay, then we'll go to this next question. Yeah. So this 10th question. A non-conducting charge ring carrying a charge of q, mass m and radius r is rotated about its axis with a constant angular speed omega. Find the ratio of its magnetic moment with angular momentum. See, what they are given is in this problem. So there is a ring like this. Okay, there is a ring. It is a non-conducting ring, but it is having a charge. It is having a charge of q, and it is having a mass of m. Okay, and it has a radius of r. So this is the condition of this ring, and this ring is rotated. Okay, in this direction, either clockwise or anti-clockwise. So it has been rotating with an angular speed of omega. What they are asking? They are asking the ratio of magnetic moment with angular momentum. So magnetic moment is Pm. Okay, Pm, and angular momentum is L. So this ratio only we have to find. Okay, Pm by L. So magnetic moment by L, that is the angular momentum we have to find out. So you know this magnetic moment for this ring will be equal to I into A. Okay, the current into the cross section. Okay, this I can write it as, because the charge is there, q with respect to time, so q by t into area. What is the area of this ring will be, the radius of the ring is r, so it will be pi r square. Okay, this is the Pm value. Then L, what is L? L is the angular momentum. Angular momentum, you know this formula, I into omega. What is I? I is the moment of inertia. Moment of inertia of the ring. Okay, what is the moment of inertia of the ring? Mass of the ring into r square. Okay, and omega I can write it as 2 pi by t, angular speed. So that is for one cycle it is 2 pi, that is 360 degree, and covers in time with respect to how much time it takes for one cycle. So that is the angular speed omega, okay, or angular velocity I can say. So 2 pi by t. So now you find out this ratio of this one is Pm by L will give you q by t into pi r square divided by mass into r square, that is a moment of inertia of this one, divided by 2 pi by t. Okay, so with this if I simplify this, okay, this pi and this pi I can get cancelled, and this r square get cancelled. Okay, this t and this t will get cancelled. Okay, so finally this ratio Pm by L will be equal to this q I will have, okay, in the numerator, and this 2 and m I will get, okay, q by 2m. So this ratio of magnetic moment with this angular momentum L will be q by 2m. So here the answer will be C. The C option will be the right answer. Okay. Yes, thank you very much. We will see in the next video with the solution of the remaining questions. Okay, thank you.